Okay, folks, to finish off this piece, what I want to talk about now are some different thermodynamic processes that you might be able to use to do heat engines. Well, there's some easy ones, the four that we've looked at that you could use, but there are other ones that you might think could be possible, right? Again, here is our PV diagram, right? Let me get rid of the negative volumes and pressures there. And so here is an initial spot, and I could go like this to spot number 2, right? And I could label this as a process, call it process A, right? This is a complicated process, right? I'm going from some initial pressure, volume, and temperature to some second pressure, volume, and temperature. And look, because we know those isobars go like this, we know that that's a different temperature. And we see that obviously it's different pressures and volumes from where it was initially. So, oh my gosh, this is a crazy kind of process. I put a flame under it, and if it was only the flame, what would occur? If it's only the flame, then it would be an adiabatic process. No work being done on the system or work done by the system. And that thing, if you recall, has curves that look like that. That would be an adiabatic process. This one obviously is not adiabatic. It's obviously not isothermal. It's not constant pressure. It's not constant volume. But the key that I want to point out here is, so I would put a flame under this, but I would actually have to be pulling on the lid, pulling on the piston. I'd have to be doing something here, right, to make this occur, besides just sticking a flame under it. Now, I could make the gas follow this curve by very carefully monitoring what's going on, so that I pull at the right rate as heat is being dumped in, so I follow that straight line that's at some slope, right? So I could do it. I'm just saying it's not that easy, right? Now you could make up cycles, right, that use processes like these. You know, for example, you could make up a cycle that looked like that. And if I did the cycle in this direction, it would do work. And now, this one is one that's easy, one that I know, constant pressure, a constant volume, and this is a wicked one like the previous one that I drew. It would be really difficult to get this to work right, and also to figure out the heat flow, right? The amount of work, that's easy. It's the area under the curve. That one kind of makes it simple to figure out that way. But those other things make it a lot more difficult. There are plenty of cycles that are out there, all right? They usually don't involve things like this, right? They use those 4 thermodynamic processes that we talked about. Constant pressure, constant volume, constant temperature, and adiabatic, right? Adiabatic process. Where, what's an adiabatic process? Where we don't let any heat flow, right? So the system changes its pressure and volume, but only through work, all right? So, in fact, let's draw up those other 2 sets that we didn't talk about before when we did cycles, and see what happens. So here is one isotherm. Here would be another isotherm, right? So here would be a cold temperature and a hot temperature. Remember, we figured that out, that the hot ones are up higher inside the cold ones. All right, so if I run along one of these, I've got an isothermal process. So let me start, let's say right here, and I'm going to run down this isotherm to right here. So here's 1 and here's 2, and here is process A, an isothermal process, right? Next, I'm going to do an adiabatic process, right? An adiabatic process. Adiabatic processes kind of look like this, right? They have this kind of curve shape to them. So here is an adiabatic, right? Going in that direction. Now, that takes me to number 3. I'll call that process D. Now I'm going to run up this isotherm with another isothermal process. Like I did the box before, right? I went over, down, over, up. Well, that's what I'm going to do here to produce a cycle. So I'm going to run across here, process C, to some spot, say right here, spot number 4, that then is going to be connected up with 1 through process D. And that process right here is another adiabatic process. So here, I've created a cycle out of 2 isothermal processes, A and C, and 2 adiabatic processes, B and D. Now, there are 2 reasons why I put this one up there, which I have labeled, of course, 1 and B. The first reason is because these processes are ones that we've talked about and ones that you could actually work out what's going on. You could work out the work and you could work out the heat flow, all right? The heat flow for 2 of these is pretty easy, right? Remember, adiabats have no heat flow. So this one and this one have no heat flow, all right? Well, that must mean one of these is an innie and one of these others is an outie. And you can see fairly easily that here is my QH and here is my QC, right? Okay, so I'm running along, absorbing heat, then I don't absorb any heat, I do some work, right? I let go of some heat, and then I do some work, right? So here is a nice cycle for us to look at, right? And so the problem is, even though you could do these calculations, they really are pretty complicated. And in fact, in the end, they take a bit of calculus to be able to work them out completely. Because there's no constant pressure, constant volume kinds of stuff. You have to do integrals to get areas under the curves. All right? So we're not going to look at that. All right? The other reason why I brought this up, B, is this is called a Carnot cycle, or a Carnot engine. And it turns out that this is the thermodynamically most efficient engine that one can have, right? It's the one that is the best, right? And if you remember from way back when, like a week ago, right? The efficiency of that Carnot engine is what? It's 1 minus the cold temperature divided by the hot temperature. And we can see, oh look, there's those temperatures, right? And if we kind of look over here a bit, I think you can still see this, right? Now we see, here's that heat going in, heat coming out, the hot temperature, the cold temperature, the work out, right? The work out then is going to be that area. Remember, the work out is the work positive minus the work negative. That's the work that we get to do out. Okay? And that we only worry about QH in, right? Not QC out. That would end up giving us this for our Carnot engine. It's the best possible engine there is, right? Heat engine. Now, I want to mention that there are a lot of other cycles that are out there. They almost all get modeled using the 4 thermodynamic processes that we talk about. Right? The Otto engine, which is, or the Otto cycle, which is what is used to mimic what goes on in an automobile engine, right? Uses those 4 processes. There's something called a Stirling engine that does the same thing. A steam engine uses what's called the Rankine cycle, which again is simply a specific set of these 4 processes to create a cycle. All right? So that's really pretty much what I wanted to say about heat engines and using, right, using the ideas of ideal gases to give us how we determine what goes on with these heat engines. So one final thing with all of this, that again, it's just mentioning it to you. What if we run this in reverse? If we run it in reverse, right? So let me just erase this for a moment, but put it back, except with the arrows going in the opposite directions, right? If I do that, I've created a refrigeration cycle, right? Because the area under the curve up on the top is negative as compared to this one positive. This means the universe has to do work to get this cycle to happen. And what we would find out is that the amount of heat flow shoved heat into the hot source, right? A refrigerator took heat from the cold sink, threw it into the heat source because we did work to it, right? So that's how a refrigerator ends up looking. It's simply the heat engine cycle run in reverse, all right? One final thing, and let me put the arrows in the previous direction just so that we don't get confused. Okay, so we're back to a heat engine here. I want you to notice something, and that is, this doesn't just run itself. All right? The gas is doing work to the universe. But here, someone has to push the piston in. Right? The universe has to do something to this gas, squeeze that piston in. Has to do work, right? It doesn't happen by itself. It turns out that the work that the gas did to the universe is more than the work the universe has to do to the gas. So it's a successful heat engine. But it's not just that here's a gas and I magically, bloop, it turns itself into a heat engine. No, right? And that's, as an example, the car engine, the Otto cycle. There's a whole lot that goes on of storing up energy right, to supply to the work, to squeeze the piston up in the cylinder, kind of compress that gas again, air-fuel mixture. Right? So it's a complicated system that goes on to take some of this energy, work, store it to be used later to help produce the cycle. So these cycles seem rather simple, but the mechanics behind it can be very complicated. All right? So that's it for the video lectures for today. Right? So remember, we went through looking at specific heats for ideal gases, for constant pressure, constant volume. We already knew about specific heats for solids and liquids. They don't care about constant pressures, constant volumes, because none of that really changes for them during the heat flow. All right? Then we looked at creating thermal equilibrium with two different materials. Finally, we looked at using our ideal gas with the idea of an engine, a heat engine, and determine how that plays out. All right? So you're all set to do the homework problems, right? To look those over, to work on them. And I want to calm you down a bit, because you're probably right now freaking out about how complicated could he make questions on the final exam with what just went on. Well, obviously I could make them unbelievably complicated. And if this were, the physics major's thermodynamics course, yes, they would be very complicated. But not for you folks, right? The best, the most exciting stuff that you need to worry about is, okay, if I put a cycle on, can you give me what's the work that this cycle does, right? And you could. You need to get the area under the curves, the positive areas, the negative areas, right? Subtracted away to find out what the work is, which is always the area enclosed in the cycle. If I put a cycle on that looked like this, you would know that it's this area. If you could calculate that area, you would have the work that the engine does during the cycle. Calculating the heat flows, I don't know, that's a little bit long for on an exam. Although, you should be able to calculate heat flows, right? From the stuff that we've done on ideal gases earlier in this video lecture stuff. Right? Also, you really should be able to, I take hot coffee and I put cold coffee in it and I get lukewarm coffee. You should be able to figure out what temperature the lukewarm coffee would be at if you know what the hot temperature and cold temperature was, right? Things like that. So don't freak out too much. Get your homework done, and I will see you on Wednesday. Hope you have a good 4th of July weekend. Thanks.